Hey everybody, this is Devi from Devi's Lab, and in this video I'm going to talk to you about some basics of small language models. Now this is based off of a blog post that I wrote and also a presentation that I gave back at work. So hope you learned something new today. Let's get into it. Hey everybody, welcome to my video on understanding the business case for running small language models on CPU. So this is going to be a really quick video to help you get started with understanding what small language models are and also understanding how they're currently being applied across the industry. So before we dive into the actual content itself, let's understand what small language models are and how they differ from large language models. So when you think about large language models, as we all know by now, they are trained on vast amount of data, and when you look into these models, they have billions and trillions of parameters. So the way to visualize these parameters are, you can think of them as adjustable knobs that the model tweaks to learn and understand the different patterns of data. So the more number of parameters, the more complex patterns it's able to get and derive from the data that is fed. So the fact that large language models have billions to trillions of parameters, and we're talking about anywhere between 30 billion to trillions of parameters, so the fact that they have so many different parameters, they are also able to learn very complex patterns in data. So this is exactly what makes them very good at handling very complex tasks. Now let's look at small language models. So small language models have lesser number of parameters. So we're talking about 3 billion to 15 billion parameters. And this is why they are able to do one task really good, because they have less number of parameters and they're able to use that knowledge and understanding very good and very well to use one task at hand. So that's a quick difference between large language models and small language models. And we'll get started with the actual content itself. So these are all the different things that we will understand. We start with some market overview, and we'll also understand what got these SLMs in the game and all the advancements that's been powering up SLMs. We will wrap up with a quick hands-on exercise as well, so we'll get started. So the first thing here is understanding the overall small language model market. So as of 2025, the small language model market stands at $0.93 billion, and it's projected to grow to about $5.4 billion by 2032 with an annual growth rate of 28.7%. And the cost reduction is also anticipated to be anywhere between 40 to 80% compared to LLM deployment. Once again, the reason is you have lesser number of parameters, so you have lesser space to occupy, and most of these SLMs are open source, so you have all the rights to go download an SLM that works out for you on Hugging Face, test it out, fine-tune it, and deploy it on your own servers. So that's the cost reduction piece, and just a quick overall SLM market overview. So let's understand why CPUs are actually back in the game. So there are three reasons or three buckets, okay? The first one is the availability of smarter models. So small language models have become really good, and the reason is just some enthusiastic effort from both the commercial players and the open source players. So when it comes to commercial examples, we have IBM, Cohere, AI21 Labs making small language models, and when it comes to open source, we have Hugging Face hosting a lot of these models such as Mistral and Llama for free. The second one is CPU optimized runtimes. So we now have advanced frameworks such as llama.cpp that have been designed exclusively for running small language model inference, which is great. And the third bucket or category here, which made SLM popular, is that we have a lot of advanced SLM optimization techniques such as quantization, distillation, pruning. So we'll look a little more detail into these optimization techniques in the forthcoming slide, but I wanted to give you a quick understanding of what are the three reasons why SLMs have become super popular once again. So there are of course pros and cons of using small language models. When it comes to strengths, these small language models, they have ultra low cost because you run them on CPUs, you don't need expensive GPUs. Second one is low latency because there's lesser number of parameters, lesser memory footprint, so it's quicker to infer. And lastly, when it comes to the strengths, it's always about privacy first deployment. You can totally get these SLMs and have them run locally or at edge. So those are scenarios where SLMs and CPUs make sense. However, there are some limitations as well. For instance, the batch size, it's always limited to 1. The whole thing behind GPUs is the power of parallel processing, which is not possible here. You also have smaller context windows as compared to LLMs, and lastly you have lower throughput. So imagine scenarios where you can't have thousands of users logging in at a time. It's more suited for low throughput scenarios. Like for instance, think of a grocery store manager who wants to check his inventory levels. So this is a classic example where it is a low throughput scenario and smaller context window, because he's just going to check his store's inventory levels. So this is a great example where you can turn the limitations into strengths. So it's all about understanding your scenario and doing a detailed trade-off with your particular business case scenario. So now let's look at some real world examples of enterprise use cases. So in finance, where compliance is everything, one multinational bank used small language models, and it resulted in 2.5 times faster processing when compared to LLMs. And this was a fine-tuned small language model. So it also resulted in 88% increased accuracy along with 80% cost reduction. So that's from the finance side of things. Let's move on to healthcare. So here again, small language models were used on device for measuring patient analytics. Think of things like variables, where these SLMs were running and they helped analyze the data and make real-time predictions on the patient's health. So that's how they were used in healthcare. Moving on to customer support and operations, SLMs such as Mistral and Granite, they helped with lowering costs from anywhere between 40 to 60%. Another example from logistics and automation was an example where they used SLMs to extract data from receipts and also to monitor package damage. So like I said, when you use SLMs for one task very specifically, they're able to do a really good job at it. These are some real world enterprise use cases of how small language models are already being applied. So see, it needn't always be about SLM versus LLM. You don't have to pick one over the other. You can actually leverage both of them strategically. And that's exactly what IBM's Granite 4.0 hybrid Mamba transformer model embodies. So it embodies this very concept of leveraging them strategically. So they have this transformer model, which is an LLM, which sits at the cloud, and it oversees a lot of small language Mamba models that operate at the edge. Classic example of how you can use this to your advantage. This is again an overview of how IBM Granite 4.0 works. Now let's understand the CPU inference technology stack. So there are two things you need to be familiar with. Let's first look at the inference runtime for CPUs. So inference runtimes are nothing but the engines that do the actual math, or you can call them as math machines. So when you give an input to a model, these inference engines, they do all the number crunching to make sure that the model serves the best probable answer to your question. Okay, so that's what inference engine or runtime is all about. Now some classic examples here are llama.cpp, which is a CPU first runtime that supports GGUF format. In a minute I'll tell you what GGUF is, but for now just understand that llama.cpp is a CPU first runtime that supports this particular format. And you also have VLLM. This was built as GPU first, but now it's been optimized to be CPU capable as well. So that's inference runtime. Now on top of this inference runtime, you have local wrappers, and you can think of them as GUI or user-friendly layers that are built on top of this engine to make interacting with the inference engine easier. Some examples here are Ollama, GPT for All, and LM Studio. Once again, you'll pick your wrapper based on the inference engine. For instance, Ollama is really good for llama.cpp, and you can use LM Studio anytime you use Hugging Face models. So those are the two things of it. At the core you have inference runtime, and on top of it you have local wrappers or launchers. So I told you how I will talk about GGUF and quantization, right? So that's the thing here. So GGUF is nothing but GPT generated unified format, and you can think about it as something that simplifies the whole quantization workflow. So what's quantization? Quantization, the easiest way to think about it is anytime you, let's say you have a 4K photo, okay, and you want to bring it to HD. So converting that 4K print to HD is going to save you a lot of space, but at the same time you lose some clarity, right? But it's not a deal breaker as well. So that's the thing about quantization. That's what's happening to the models as well. They are originally in 16-bit format, precision format, and you bring them down to 8-bit or 4-bit. So that's what happens in quantization as well. And this GGUF, right, or GPT generated unified format, it simplifies the whole quantization workflow, and it compresses and packages your model in one step. Another call out here is that this GGUF, it's purpose built exclusively for inference. It has nothing to do with training of the model itself, but it's all about improving the inference efficiency. At the end of the day, you have a single portable file that loads anywhere, anytime. And there are also some benchmarking studies that have been done, and they found out that 8 billion parameter model quantized to 4-bit gives you an optimal balance for most production workloads. And they also found another sweet spot for CPU deployment. Again, these are all benchmarking studies, and you can also look through and do your own research for your own specific use case. So when it comes for ultra low latency use cases, they found that 4 billion parameter models quantized to 8-bit did really well. So that's a quick overview of GGUF and quantization. Now that you understand quantization, I also want to talk to you about two other optimization techniques, such as distillation and pruning. Quantization is one optimization technique, and then you have distillation, or knowledge distillation to be more clear. This is when a small student language model learns from a large language model. That's knowledge distillation. And you also have pruning, where you get rid of just like how you prune your plants, you get rid of the excess stuff and you keep only what's necessary. So those are the other two optimization techniques. So how does this all translate from theory to practice? There's a simple 4-step process that I've given here. First is you actually understand your use case, and based on that you pick the right small language model. So once that is, you'll start with a local setup. Here you will build llama.cpp and start up the server, and on the front end you can have a simple Streamlit app which is going to help interacting with small language model easy. In this example, I built a small translation app using this 4-step process, and for this I used Mistral 7 billion model from Hugging Face, and I'll also give you an overview of this model real quick. But here again, you start with local setup, which is all about building llama.cpp and starting the server up, build a front end, and then you make sure you test locally, validate your use case, and make sure that it actually answers your question. And then you have the option to either run it locally on your machine if it's just for your individual use, or to deploy it to EC2 with the manual install or Docker. Now let's take a closer look at the model that I use, which is Mistral 7 billion instruct model. So the method that's been used to optimize this is Q4KM quantization. Now let's look at it. Let's break down and understand what it really means, right? So Q4 precision here is, instead of the original 16-bit, it's been quantized to 4-bit precision. So this results in 75% reduction, bringing the model down from 14 GB to just 4.4 GB. The next one is K quantization method. So this is one of the advanced method that intelligently preserves the most vital or important weights, and this results in 2 to 3 times increase in speed. And of course, the last thing about quantization is all of this helps with running your model offline without any internet required. Alright, cool. That's it for today. In the description, I've linked the short series that I did on this and also the blog post that I wrote. So I'll see you again in another beginner friendly AI video. If you like this content or if you found it helpful, consider hitting that subscribe button. I'll see you soon in another video. Bye.